just be going over all the chapters that are going to come in the exam. I'll start with chapter 9. So we have flexible drives over here. So let's start. So let's scroll down and see what we have over here. Part A. We have introduction generalities. We have the mechanism dates back to 100 years. Yes, we know this. Transmitting power. So the great majority of mechanical power transmission involves rotating shaft. Rotation is continuous. Okay. Matching a prime mover load thus involve the transformation of power between shafts. So we're gonna just take this and put this into our own words. So what are we saying here? We're saying that when we have a driving shaft, this usually has a high N RPM and a low torque. Okay, this goes on to be reduced to a load shaft with a low N RPM and high torque. Okay, through a speed reducer ratio of R is greater than 1. So I'm just gonna yoink this from here to here. Let's bring this over here. Okay. Next, let's look at what we have over here. So we have transmitting power, gears, shaft, and bearings. Right now we're looking at flexible drives. So why are they so important? Why do we use them? So we know that we use them because they're good over long distances. Shaft alignment is less critical, quieter, absorb short loads, and also vibration. So this and this are going to stay together. Lower cost is economical. Reverse directions, they haven't shown us the figure yet, and multiple shafts. Okay, so from this, I'm just going to write over here, for example, maybe let's change the header to body. All right, okay. So with this, so flexible drives. So the cons are used over long distances, lower cost. I'm putting this in order to how I would remember it. Lower cost. What else is quieter, right? Okay, what else can we say about this? Okay, isolate vibration, and then I'm gonna write so it absorb shock loads. Okay, what else do we have? We have your shaft alignment, that's critical. I'm not going to remember that, to be honest. Reverse directions, probably I'll remember this, and multiple shafts. Okay, that's all I'm going to remember for why we use flexible drives. So we have belts and chains now. So it's a better alternative to gears. Okay, so now we're looking at belts and chains. So just belts, I guess. Belts, chains. So they are economically better compared to gears. And why so? So for example, maybe this here. So why are they better? So we can say this is better because they can be lighter, smaller, and efficient as the gears. But let's change the color here. So the life is limited. All right, cool. So I can't spell. Just gonna ignore that. Okay. Belt versus gears. So we have when two gears are meshed together, directions of rotations are both the other opposite. Yeah, we know this. So two pieces connected by a belt will rotate in the same direction. So this is just a figure. Let's put this figure here. So you remember this. So this is your gear versus belt drive. All right, cool. So that's part A done. Let's go back. Let's go part. Oh no, what's going on here? All right, let's try now. There we go. Okay. So this is part A done. Let's look at part B. So part B, we have belts. So now we're looking purely at belts here. Okay, lots of words. A belt is a flexible band. Okay, so that's pretty much it. That transmits rotary motion from one shaft to another. Belt transmits motion as your gear turns, but belt drives are better for greater distance with smaller forces. We already looked at this. Oh, okay. So let's add here. Let's add for example, let's add a text box here. If I can make one. I cannot make one, so hold on. If I can, there you go. Okay. And yeah, that does not work. Okay, I'll just write it then. So with this, we have a flexible drive. So this, I'm gonna write to the addition of this, greater distances. I'm just gonna write smaller forces. Okay. Belt is a flexible band, so I'm just gonna write belt over here is a flexible band. Okay. The belts are installed with substantial tension to create friction that allows the belt to grip the pulleys, allow them to keep them from slipping as they turn. Well, this seems important. Okay. So, oh, I didn't write part B. Okay, give me a second. Let's add this here. Go back to text. Control C, Control V. Yeah, part B. All right. Okay. So belts are either flat or exist in V-shape cross section running on grooved pulleys. V belts require less tension than do flat belts because they. Oh, this. Okay, this sounds important. All right, let's write this down. Okay. So we have over here. So belts. One, either flat. Okay, flat or two V-shaped cross section on grooved pulleys. I don't know what grooved pulleys are. I mean, right now I don't. Maybe later. Okay. So V bolts require less T than flat bolts. Now why? Because let's change the color. All right, because more surface area contacting the pulley, so more. Okay, more. Okay, so more friction. Okay, good. Let's go down now. Belts. What's the condition for a belt? So this was flexible drives. Now we have belts. What's with belts? Okay, let's go over here. Then scroll down here. Okay, go across. This is not a caption. This is body. So can you please change this? Okay, and go back to this. So belts require. Okay, small pulley dia. Okay, I'm gonna write dia. Then we need, what do we need? We need high belt surface speed. So I'm guessing N should be high. Oh no, belt speed. So okay, so V should be high. Low noise. This is 3. Low noise. Then we got 4. Low weight, subject to creep. So I think this will be asked, to be honest, for the creep part. So creep is, let's change the color to red. Red, there we go. Okay. Relative motion between the pulley and belt surface. Pulley and belt surface. Tensioning device needed. So I'm guessing this is for, so it's not slack. That's what I'm guessing from this. Okay. Types of belt drives. So I'm going to draw this so I actually remember this. So we have types of belt drives. So let's go back here. So we got types over here. So types of belt drive. So we got flat, standard, flat, and if I okay, all right. Let's draw a better one. Okay, that's your flat belt. Okay, then we got round. Round. That's a circular. That is not a circle. Alright, round, we got V bolt. So just, okay. And timing belt. Timing belt. So this is when you have a straight line, then a small, Okay, this reminds me of, and then there's a little here. Let's just actually zoom in. What does it say? What's it saying here? P. So I'm guessing this is the pitch diameter or pitch radius. P to P. All right, cool. All right, let's go. Then this is just an example of an automobile drive belt. Okay. Flat and round V bolts. So flat round bolt work very well. Flat bolt work must under higher tension than V. True. Okay. Therefore, they require rigid shaft, larger bearings. Okay, this seems important. So what I'm going to do is I'm gonna type it up. Okay. So within the flat belts, we have. Oh, let's go up here. Actually, here. So we have flat belts are must work under a higher T than V belts to get the same to transmit same torque as V belts. Okay, maybe I should write tension here so it's not confusing. V belts. So okay, cool. Therefore, they require more rigid shafts. So this means more rigid shafts, larger bearings, and so on. Okay. V belts. What's so special about V belts? V belts create great friction by wedging into the groove on the pulley or sheave. So that's a key word. Maybe we'll be asked about this. So V belts. More friction because wedging onto the groove or into the groove on the pulley or sheave on the sheave. Okay, so larger friction equal larger torque capacity. Okay. Now, flat bolts are made out of joint hide surface to rear. Okay, this is, yeah, okay. Do we mention they're good for high speed? No, let's just, have I mentioned it anywhere? No. Okay, so the thing is, where are they gone? Yeah, so they're good for high speeds, so they're suitable, so let's write suitable for a high end. Suitable for high end. Alright, cool. Flat belt pros. So maybe let's move this down here. Okay, so pros. Simple. Both sides can be used. And a high P at a high N. Alright, cool. Cons. Bulky, require lots of tension, otherwise slippage. Okay, what else? Belts can slide sideways, so belts can slide sideways on the pulley. Okay, that makes sense. Sideways on the pulley. Alright. Characteristic of flat belts: you have concave crown, convex crown, concave crown, straight taper. Okay, I'm just going to yoink this and put this here. Okay, let's see if there's enough space here. Let's go back here. Maybe it'll be easy. Yeah, there we go. Let's move this down. Yeah, let me move this up. There we go. Okay, let me make this a bit larger. Go to text. Let's move this down. All right. There we go. So. Okay, V-bolts, there we go. Okay. Non-reversing and reversing belt drivers. So what is this? So non-reversing open belt, reversing crossed. So why is it non-reversing? Is it because it's not crossed, or what's the reason for this non-reversing? Alright, okay. So let's search up. Over here, non-reversing open belt, non-reversing open belt versus reversing cross belt. Okay, just need a answer here. When in doubt, just check ChatGPT. So we have non-reversing open belt versus reversing crossed belt. So the main difference is that both pulleys are in the same direction. Okay. Open loop, the belt is triggered figure 8. Opposite, so it's reversing. Okay, yeah, so it's because of this cross, so it's cross, so we're reversing that direction. Okay, that makes sense. Okay, so let's just make a note of this. So let's bring this down here. All right, with this, what we're having over here is that this crossing, so this part here is resulting in this reversing. What else? Okay, so the direction of rotation is different. Yeah, we know this. So it's reversing. This is open loop. That's why it's open. This is crossed. Okay. Then we got a shaft direction is parallel. So you can see this is parallel to the shaft here. This is also parallel to the shaft here. Power transmission. This one is supposed to be apparently power transmission should be higher because of angle wrap. So there's more wrap, higher wrap, but that's just what GB is saying. Anyway, let's go more. The characteristics of flat belt. So this is a quarter twist belt drive. So when you have a twist, it can go down at the midpoint. Okay, that's fine. Characteristics of flat belt. This driver eliminates the need for a clutch. Flat belt can be shifted left or right by use of a fork. Okay, that seems important. So we have a fork. So he's gonna yoink that here. And let's just type here. So no, actually let me just do something like this. So this driver, so we have a the shift fork can move the flap belt left or right. Okay, now we have V-bolts. So V-bolts are composite structures made out of nylon, rubber reinforced nylon, rubber high coefficient friction fibers, can carry high loads. Okay, so is this something that I need to write down? I don't think so. I think maybe no. I think that's fine. Because V-bolt, each component of V-bolt performs a particular function. The main carrying load are the tensile members. So I'm guessing these tensile cords there. Actually, no. Let's just put the diagram, so we have an idea. Of this part here. So this is V-bolts. We'll just quickly do the V-bolts here. So now we're doing V-bolts. Okay, this is still flat. So let me just clarify. That's still flat. Okay, now we're doing V-bolts. So we have an angle between the grooves. So this angle here, I'm guessing, from here to here. This groove. Okay, correct. Too low, too high. Now, I'm guessing we're going to be asked to draw something like this. So the groove semi-angle lies between 17 degrees beta and 20 degrees. It should be noted that there is a gap, i.e. no contact at the bottom of the groove. Okay, so let's actually write this down. So this figure can come, and why is this important? This is because, so over here, so let's just, okay, with this no contact at the bottom of the groove. All right, and the groove semi-angle. So is this angle here from here to here? Because they're saying the groove angle between this. Oh wait, no, it is. It's okay. It's this here to here. So if you imagine, okay, so okay, what I'm imagining is if, for example, you have a triangle, and this carries on from here to here. We're talking about this angle here being 2 beta, and so beta needs to be between 20 degrees and 17 degrees. So basically this length needs to be between 34 degrees uh, and 40 degrees. Okay, understood. V-belts. So what are the pros? Let's quickly write the pros here. So pros and cons. So we got body, and we'll just write this in. Pros. Pros. What are the pros? So we have they're very very resistant to tension. So high tension resistance. High resistance to tension. And creep. Now what is creep again? Let's go back up. So creep was, I think I wrote this down. Here we go. Relative motion between the pulley and the belt surface. So relative motion between this pulley and the belt. So is this moving? Ah, okay. So is the belt moving different? Is belt moving a certain way, and then the pulley moving a certain way? It's very resistant to the creep. Okay, cool. So let's write that down. All right. So tension, creep, and good durability. All right. A relatively high mechanical efficiency. So just write high. If oh no, okay, high mechanical efficiency, like 95%. No lateral slippage. Okay. And best combination of traction speed. Okay. I don't know. I think that's just that's not really that important. Cons. Cons. Not suitable for not suitable for small pulleys. Need to bend to accommodate so pulleys. Why? Because need to be able to bend to accommodate groove depth. Groove depth. Okay. Alright, so let's compare them. So flat bolts have efficiency equals 98%, same with what gear drive. V bolts about 70 96, but they can transmit more power for a similar size. Okay, so now I'm just gonna write here for my pen here. Okay, flat V belt. So valve can have efficiency equals 90%, so 98% efficiency, and then we have 70 to 96% efficiency. Low and but this for power, same size. Okay, same size. It can transmit more power compared to this. So okay. In low power application, most industries use the cheaper install Cosmins versus their great efficiency. V-belts are very common. So just quickly write this. This is cool. Wedge belts are narrower and lighter than V-belts. Centrifugal effects which reduce belt pulley contact pressure and helps friction torque, and therefore not so deleterious. What? Oh, not deleterious. Causing harm or damage. In wedge belts, therefore not so causing damage as they are in V belts. Okay, is this something we need to know? Okay, I'm just gonna quickly write this. Let's just write a text here actually. Okay, we have wedge. No. So we have wedge belts. Okay, let's try that again. wedge belts. Wedge belts are narrower, and lighter than V belts. Okay, cool. What else do you know about this? Okay. Which centrifugal effects reduce belt pulley contact pressure and friction torque are therefore not so harmful. So with this, we know that centrifugal affects lower contact pressure. So frictional torque, torque is not as harmful in wedge bolts than V bolts. Okay, so that's it for V bolts. So just quickly, and we'll just put a diagram there. Okay, so it's narrower than, so this is your comparison to, so let's put it beside it, so something like this. Yeah. Okay, and let me, okay, see if I can, yeah, there we go. Alright, this is comparison. So our V bolt is here, so this is V bolt. This is wedge belt. Okay, this stuff we don't need to know. I'm not remembering this. V bolt cross section, yeah, okay. Cut belts, so we have modern material cut belts to dispense separate cover. So we have cogging, so it's the belt illustrated also. So this is the belt illustrates, and this is the belt illustrates. Cogging, which lighten harmful belting, such as stresses as the belt is forced to conform to the pulley curvature. Cogging should not be confused with the teeth on timing belts. So this is cog belt, so V belt design, V belt pulley. Okay, so just gonna write here. We have cut, cogged belts. Now with this cog belts, what we have is something like this. No, not like that. Something like this. Okay. And then what happens there is that this should not be confused. So what this does is you have cogging. And what this does is it reduce harmful bending. Okay, so that's cogging. Alright, cut cog belts, yeah, okay. Round belts, they're versatile, simple, reliable, small torque, medium velocities. Their main advantage is poly-direction flexibility. So we're just going to, no, actually no, we're not going to use that. We can just write it up because we don't need all this information. Okay. So round belts, it's in the name, I don't need to draw it. They're simple for small torque and medium velocities. No, right, medium velocities. Main advantage is poly. So I'm just gonna multi-directional. So it can be in multi-direction. Okay, there we go. All right, velocities. All right, let's correct that. All right, cool. There are two types. So we have homogeneous round belts, middle material, and round belts with tension member. Okay, so two types. One is okay. I was gonna write one material belts. So rubber / plastic. Two is belts with tension member. Okay, what is this? Two. Okay. Okay, that's round belts. I don't need a picture of this. So timing belts. So what's wrong with timing belts? So synchronous timing belts are positive rather than friction, as they rely on gear like teeth. So they're mentioned here only for complete. We shall not examine them further. Okay, so that's fine. Timing belts, tooth or signature belts do not slip, therefore they transmit torque as a consideration, which is great for application requiring precise time, such as driving automotive camshaft from the crankshaft. Very efficient, more expensive than other type of belts. So okay, so this is the main thing from timing belts, does not slip. Okay, so let's write that down. So we will have here timing belts does not slip or stretch. We have constant angular velocity ratio. We also said they're expensive compared to other belts. What else did we say earlier? We said that from here, toothed or synchronous belts don't slip, so we also don't slip, they transmit. I'm gonna write why they don't slip, because they are toothed. Okay. Very efficient. Okay, so efficient. Alright, cool. I'll go down. Pros: positive transfer belts, so it can track relative movement. So even cog belts. So okay, let's write over here. Cog belts. Okay, let's quickly. So cogged. There are no slippage either. Okay, cool. Often used to serve gear the chain, so they're relatively very quiet, don't need lubrication. So let's just write over here. So no, it's a quiet, no lubrication needed. Okay, okay, needed. Okay, anything else? Needed least tension of all belts, or okay, need the least tension of all belts, and are among the most. Okay, cons. Let's do them in red. So cons are more expensive. We talked about expensive. Special fabricated tooth pulleys. Yeah, we did that. A lack of clock action belt would not progressively disengage. More intention release design, more consideration. So okay, so need. Okay, so you'll have to write here for red. So you need to do what? You need to design specific. Design specific. And more dollar. Okay, done. Okay, rib belts. So these belts are featured when a number of ribs/grooves that run along the length of the belt. The pulley has matching ribs. Okay, found in many applications. Very common in modern vehicles. Okay. Okay, so I'm just gonna attach one picture, and then I'm just gonna write what we need to look at. Okay, so I think, hold on, what other belts are there? Are we doing to all of them? Oh, okay, we're almost done with part B. I think part C is just theoretical, which we'll quickly cover. Okay, cool. So rib belts. So we're at the rib belts now. So let's go down. So we have over here. Let's add another one. So we have rib belts. Okay. Alright, so we're just going to say they have no feature. No, it's right here. Feature or have a number of grooves that run the length of the belt. Okay. Pulley has matching grooves. Okay, this is intended to provide more contact area, the better grip, less slippage. Yeah, okay, so we'll say, so let's write this in black. Okay. The pulley also has matching ribs along its circumference, which is your obviously the length. So what you get is more contact area. So better grip, less slippage. Okay, maybe if I can. Okay, can I not? and then move this across. Okay, okay, I think I can just, alright, cool. Okay, let's found media application, so let's put a picture of this. So you have your matching things here. Let's bring this here. Okay, let's look at pros and cons. Let's go down, blah blah blah. Okay, let's put the pros. Let's put the pros here. Okay, pros. What are the pros? Pros. Immune distribution. Okay, so tension is evenly distributed. What else? Good load, power capacity. Okay, so just write good. Okay, I don't know what good load. Good. Good. High power capacity. Okay. Sometimes possible to drive off the back of belt. Long life. As due to reduced vibration, and you have stability of the drive tension. Okay, we'll go here. Cons. Okay, require specially fabricated material, which makes sense. Fabricated rib pulleys. Alright, cool. Conveyor belts, yeah, okay, we know them. Metallic belts, yep, multiple belts. If a single V belt is inadequate, then multiple belts corresponding pulleys are necessary. Okay, cool. Variable speed belt drives continuously variable, so the fork you can tune it to go up and down. Okay, if that's the case, so decrease speed drill press. Okay, so so what we can say is there. Okay, so we can say that over here, let's just add a column here. Variable speed belt drives. Variable speed belt drives. So what do you have here? We have they are continuously variable, continuously variable. So uses fork to shift between shift left or right between the different speeds, which makes sense. Okay, and we're just gonna quickly show the picture over here. So alright, cool, and here we go. Okay, yeah, that's fine. And part C now, theoretical aspects. Okay, let's write here part C. So let's go back here, blah blah blah. Part B, part C now. Alright, so let's write part C here. Let's move that across. Alright. Hey, what's going on here? Okay, sure. Here we go, part C. And let's move it up here now. Okay, so we don't need to know this. We don't need to know this. What we do need to know is the velocity of the belt. Yeah, V1 equals pi d1 n1 over 60. So we're just gonna quickly yank this. We're gonna put this here. Control V. All right, cool. Okay. When there's no slip, they're both equal. Okay, that we already know. Yeah. So what we need to know here is that the N2 over N1, they are, so this is what we need to know here. Alright, cool. When there is a slip, so I'll write here. So for example, this is when we do have a slip. So this is when we do have a slip. So okay, so for example here. So this is, it depends on how much, at which drive. So say S%, let's say 3%. You're gonna do N2 over N1 equal d1 over d2, and 1 minus, so it'll do 1 minus 3 over 100, which is 0.97. 0.97. It depends, so this depends whether this is on each drive, pulley, or not. So for example, if it's in each drive, then you have to do it twice, 4 and stuff on. So consequence of incorrect tension too weak, high transmission, so let's write it here. So we have this right here. Let's do, instead of header, let's do body. Okay, so tension weak, get no transmission. Transmission of motion, tension too high. We get a multitude of stuff. We get no, we'll do it breakage, vibration, bending, and bearing breaks as well. Okay, cool. So breakage, vibration, bending, and okay, no, if bending shafts. Okay, shafts, and yeah, breakage of this is for the belt. Okay, so belt breaks, shaft bends, and bearing breaks as well. Alright, belt vibration. Okay, so this is important. So this one is the driver. You can see here, this is the driver. So what I'll do here is I'll just take a picture of this and I'll explain what's going on over here. So this is the one that's being spun. You see this? This is the one. This one has an N here. So this is the driver pulley. Okay, this is being driven. So whichever side is being pulled is the driver. Let's say it's rotating this way, then this side will always be tight. So for example, if you had a different setup where you had this as the motor and this as the pulley, and it's rotating this way, right, in the opposite direction, then this side will be tight and this side will be slack. Okay, and this is assuming that direction is here. Okay, all right. Maintaining belt friction. So what they do is we just add a idler pulley. So it's right here. So you can add idler pulley here. So it's right here. This goes here and this goes here. This is called a idler pulley. Okay. What else? And that's it. So coefficient friction reports on the angle of wrap. Initial tension, yeah, that's fine. Okay, if there's no friction, same tension on both sides. So T1 equals T2. Different tension on both sides. So a very key thing here is, so we have over here, so we have T1. So this one is, T1 is always your max. And T1 is always your max. Okay. So that's just something we need to know here. That's what we normally assume. Belt friction, all the stuff is not relevant. No. Alright, this is irrelevant. So this formula over here. So T1 over T2 equals E mu as phi. And this is for when you know, this is when you don't have FC. This formula here. Okay. When you have FC, then we have to use this formula here. So I'll just quickly just go over here. There we go. Don't even need me to draw it. Okay, cool. Yeah. And this part here. Torque. And don't confuse the torque with this power. This is tension. Okay, they're both tensions. Okay, let me just put it here. Alright, cool. Part D. Okay, so properly installed belts require minimal maintenance. V-belts are more reliable. Okay, we listen to them. They speak to us. Misalignments of belts, correct. Okay, so this is probably what we will be asked about. For example, so what are some common problems? So this is some common problems. So let's just write over here some common problems here, and let's type it out. Okay. Okay, let's do caption. Less text wasted. Okay, so we have, what do we have problems? So we have achieve where, dust, dirt. So this leads to debris. What else? Misalignment. Overload. Okay. Misalignment of belts. What happens is vertical angle alignment. Okay. So misalignment of horizontal angle. Parallel misalignment. So okay. Correct alignment. So okay. So this makes sense. This is in the name. Okay. This is not something hard. Part E, we have chains. So if they're flexible. Okay, converted belts, they transmit more power for a given size, more precise speed ratios. But like belts, they have shorter lifespan, and we can cause, because they're not flexible. We have roller chains, bicycle transmission. Okay, so for chain drives, okay, let's look at this. Let's add a chain drive here. Chain drives here. Okay, what does it look like? Let's look over here. This is your chain drive. Okay. With this you have pros. So what pros are we going to write here? So pros. We have higher. Oh, support more demanding conditions than belt. What? What does that mean? Support more demanding conditions than belt. Oh, you mean like higher power transmissions? Yeah, I think that's what I mean. Yeah, because they can transmit more. Okay, so higher conditions can be met, i.e. more power for same size. Okay, what else we have? No slippage. Okay, what else? A higher efficiency, long life, cheaper than gears. Cons is more noisy, limited impact, high linear. Okay, yeah. Lubrication is essential. Okay, I think that's it. Maintenance now, part F, flexible shafts. Okay. Flexible shafts, what they do is they turn around corners, damage around corners, flexible shafts. Okay, cool addition, the cost. Okay, that's it for. Okay, so one of the gear. So this is the last slide. Okay, I think if we can just copy this. Flexible shafts. Okay. So one of the greatest limitations of solid shaft is that cannot produce around corners, belt, chains with gears with bearings supporting work, transmit around corner, or we can just use flexible shafts. So instead of using all this, we can just use flexible shafts here. In addition to elimination of cost apart, it may reduce noise considerably. So we'll just write here text. So elimination of costly parts, and can also reduce noise. Okay, cool. All right, let's stop it here.